Hello everyone, welcome to this session, which is again talking about the stiffness matrix. So we are going to be talking about how to develop the stiffness matrix, what is the function of that, and this is to build up on the two previous lectures on the stiffness matrix. So why do we even worry about the stiffness matrix, and why this is important? Because it's basically very helpful when you are dealing with the computer program. So it's easier to analyze structures. You have two methods, as I mentioned before. You will have the flexibility method, and you are going to have the other one, which is the stiffness method. And the stiffness method is the one that we are most focused on. This is the only one that we're going to be talking about. The flexibility method we are not going to be touching in this class. Stiffness method also can be referred as displacement method, and we're going to explain the basic fundamentals of using the stiffness method for analyzing the structures. It's a very powerful tool, and you will see that what we're going to be showing is how the direct stiffness methods can be used to analyze the structures. Although it has very tedious procedure if you do the hand calculations, but when you're using the software, the computer software, it's very easy and very powerful, and gives you the deformations and gives you the stresses and the forces in the members for beams, frames, and trusses. So we are going to be analyzing plane stresses, trusses, and we are going to be analyzing space trusses if you wish, if we have time for that, but mainly plane trusses. And we're going to be analyzing beams, and we will be analyzing frames as well. The whole point is how to establish this matrix for the equilibrium. Bottom line, just to remind you from physics and from statics, if you remember that you have force equals K times delta. So this is the stiffness that we're talking about. If you have a spring like that and you apply the load, force F, and you have certain deformation delta, so this stretched by delta, so K times delta will give you the force. That is the basic fundamental concept behind that. But instead of an element or a spring, the K will be for the whole structure, for a member, and then you assemble that to get it for the whole structure. So the idea is how to find the K, and we call it the K, the matrix of the stiffness matrix. How to partition it, how to solve it. We need to partition this so that we'll have or we'll be able to solve for the joint displacement and the reaction. So this is something I just wanted you to understand, that what we're going to be talking about. The types of structures that we're going to be using look as such. The beauty of this is that if you apply the load for this structure, for instance, and it is going to be moving certain deformation, that software is very powerful to analyze this truss and this frame and be able to find out the deformation that you have. This is something that we're not able to find easily using the conventional structure analysis. You can, but it's very hard. But using this method of direct stiffness method, we'll be able to find the deformation. You will be able to find the moment and the shear and everything in this element. This in this frame. This is one type of structures, which is a frame. You will be able to analyze it. The other type, which is even simpler, which is the first one that we're going to be dealing with before the frames, is the truss. So the truss, as you can see right here, if you look at this truss, you have a pin support right here and a rocker bearing support right here, and this is basically a very simple and straightforward. That method will give you the forces in every member and will give you the deformations as well. From statics, from analysis of structures and mechanics of materials, we will be able to find the forces, but we didn't even touch much on the deformation. Here you will be able to find the deformation. You might argue and say, no, we studied the virtual method in structure analysis that gives us the deformation. Yes, but how about if this is a pin support and another pin support right here. So this is externally statically indeterminate. And in that case, the conventional method is not going to be very easy to use, but using the stiffness method, you can analyze indeterminate stresses and determinate stresses as well. So these are all kinds of structures that you will be able to analyze and work on. I need to summarize to you again the differences between the two methods that we talk about, the matrix two methods, which are the stiffness method, which is the one that we're going to be using, which is displacement method, and the flexibility method, the one that we're not going to be using, but it's using forces. Both methods are building on what we studied earlier. We studied the virtual work method, and that is to find the deformation in structure analysis. And there are other higher level kind of structure analysis topics like slope deflection. You don't need to worry about it. But what I want you to focus on is that the stiffness method, which is a displacement method, it will deal with displacement rather than the forces, and you will be able to find the unknown quantities, whether they are deformations or reactions. And the powerful aspect of this method is that you will be able to analyze statically indeterminate structures along with statically determined structures. So this is really nice, and that method enables you to get the displacement and forces directly. What do I mean by that? In the flexibility method, you do not obtain that directly. So this is a very easy one. It's much easier to formulate the matrix. It's much easier to do the computer operations in this method. So I just wanted to highlight to you what is beautiful about this method, and we are going to be able to download that software and use it. So this is basically dealing with, again, the stiffness matrix that you can analyze 2D and 3D element. And that's another thing that I didn't mention earlier, that you will be doing space trusses if you wish. You can do 3D elements. You are not able to do that using the conventional methods that we use in structure analysis. So this is a very powerful method that you can use. How does that work? I mean, let's agree on some concepts and some terminologies so that we are able to understand this when you start reading through the textbook or any other resources that you have. The basic premise of this method is that you're developing the element stiffness equation, meaning that you will have a load vector, displacement vector, and stiffness matrix. So you're going to have a load vector, and you're going to have a displacement vector, and then you're going to have a matrix or a stiffness matrix, which is the K that we are talking about. This is basically the whole idea behind it. And then this is for every element, meaning that for this element and for this element, for this element, for this element, for this element, you will have a matrix for each one of them, and then you assemble them all together to create the model of the whole system, the whole structure. All right, that's the whole idea. How can we do that? The stiffness method, it's requiring subdividing the structure into a number of basic elements. In this case, here is one element, second, third, fourth, fifth, and you can even analyze small pieces, or rather divide that into smaller pieces if you wish, and do the super position in order for you to get and assemble the total or the global stiffness matrix of the structure. And that is a very powerful tool, and instead of writing the compatibility equations in terms of the unknown redundant forces and flexibility coefficients, all you need to do is write the joint equilibrium equations. In terms of what? In terms of the unknown displacement, joint displacement, and stiffness coefficient. From that, you will be able to get the member and structure matrix, the small k for, so we can have the small k for the member, and then you're going to have the bigger k, uppercase K, for the structure in total. And if you are talking about truss member, then K will relate. What does K mean in that case? It's relating the axial force to the axial displacement, which is again from force equals K delta. So what does K mean? It's relating the actual force that's applied at the ends of the member to the axial displacement that's being developed. So what else do we need to pay attention to? Something called the local coordinates and the global coordinates. So if I have this element right here, I can say this element right here, it has the local coordinates x prime and y prime. And then for the whole entire structure, I have the global big X and big Y, which is a coordinate system for the whole entire structure. And there are some ways in order for you to relate the local to the global stiffness matrix. So this is something I also want you to be aware of. So let's start something else, which is again expand a little bit on the applications of the stiffness matrix and how do we subdivide the structure into smaller and more series of discrete finite elements, and then identify the endpoints. The endpoints for the structure, we'll call it nodes. So if you have the truss that looks as such, each one of these intersections of the members, we call it the nodes. So these are the nodes or the joints that we're having right here. For the force displacement methods, we would like to find out the properties of each element. I mean, the length and the cross-sectional area, so that we can find the forces that we are and the deformation that we're looking for. And then we relate to one member to another, using the force equilibrium equation written at the nodes. So the relationship between these forces and the displacement is the K that we have been talking about earlier. And the unknown displacements of the nodes can be determined for any kind of loading configuration for the structure. Once you find this displacement that you're having, then you can find the external forces in the structure, and you can calculate that using the force displacement reactions. Again, let's get back one step. If you didn't follow what I'm saying, we are going to find out the deformations first, and then we will find out the external forces or the reactions from the force displacement relationship. So that is it for this session, and I'm going to continue talking about that in the future session. Thank you.